All right, so we've all played around with AI, right? They can chat, they can write stuff, some can even code. But what's the real next step? We're talking about moving beyond just being a conversational partner to becoming an active agent that actually does things for us. So let's dig into how we go from a simple chatbot to a true digital assistant. And that brings us to the big question, really. We know AI can talk, but can it act? I mean, it's one thing for an AI to tell you how to do something, but it's a whole other ballgame for it to actually do it on its own. How do we bridge that huge gap between talking and doing? Well, lucky for us, a really brilliant new paper from the Army Research Laboratory basically gives us the blueprint. It's called Language Model Agents, Current and Future Trends by Michael S. Lee, and it breaks down exactly how we get from a simple language model to a real functioning AI agent. So we're going to walk through the key ideas together. Okay, so first things first, we got to understand the core of any agent, right? And that's the language model, or LM. The best way to think about it is like this. It's a brilliant, brilliant brain, but it's totally isolated. You see, a raw LLM is an absolute wizard with text. It can tear through documents, answer incredibly complex questions, even write poetry. But, and this is a big but, on its own, it can't interact with the world at all. It can't run the code it just wrote. It can't Google something it doesn't know. Heck, it can't even save a simple text file to your computer. It literally lives inside its own universe made of text. And here's where the paper gets really interesting in how it describes this limitation. It calls these raw LLMs stateless, which means they have no memory of anything beyond the immediate conversation. The author uses this incredible medical analogy. He says it's like they have anterograde amnesia. They're just living in this one single moment, defined only by what you just gave them. So, if the language model is this brilliant but amnesiac brain trapped in a jar, how do we get it out, How do we give it a body so it can actually interact with the world? The answer, and this is the key piece of the puzzle, is something called an orchestration layer, or OL. So think of it like this. The OL is the software that acts like a nervous system. It's what connects the LLM brain to a set of tools, and it's what allows it to, to sense and affect its digital environment. And the paper has this just brilliant analogy to help us get it. Think of the LM as the brain's cortex. That's where all the high-level thinking and decision-making happens. The orchestration layer, that's everything else. It's the rest of the brain that handles motor control, sensory input, and the entire body, the hands, the eyes, the ears that actually get the job done. So how does it all work? Well, it's this constant four-step cycle they call the control loop. First, the LM, the brain, decides what to do. It thinks, okay, I need to run this piece of code. Second, the OL, the body, hears that command and connects to the right tool, say a Python interpreter. Step 3, that tool actually does its thing in the environment. And finally, the LO brings the result, whether it was a success or a big fat error message, right back to the LM so it can decide what to do next. It's a loop. Okay, and this is where it gets really, really cool. Once you give this brain a body, this orchestration layer, what can you actually put in its hands? What's in this agent's digital toolbox? Well, the paper lays out a whole bunch of them. All of a sudden, the agent can write files to your computer. It can execute Python code to do calculations or even create graphics. It can use a search tool to look up stuff on the internet, current information. And with the newer models, it can even have a look tool to analyze an image. It has senses. It has hands. Okay, so theory is great and all, but let's see how this actually works in the real world. The paper actually walks through a few test runs that show an agent taking its very first steps, which is pretty awesome. So the researchers gave the agent what sounds like a pretty simple task: generate a wireframe torus that looks like an edible donut. Now, this is a great test because it requires not just the ability to code, but also a little bit of world knowledge and even some aesthetic judgment. It has to know what a donut looks like. And this is where that loop we just talked about becomes this powerful problem-solving engine. See, the agent doesn't just try something once. It attempts an action. It observes what happens, even if it's an error. It analyzes what went wrong, and then it tries again with a new, corrected plan. This is literally autonomous learning right in front of our eyes. So, what happened in the actual test? Well, the agent's first try at writing the Python code, it failed. It had a simple syntax error. But here's the magic. Instead of just stopping, it read the error message that the ALL fed back to it, it understood the mistake, and it rewrote its own code to fix the problem. And on the next try, it worked perfectly. It debugged itself. No human had to step in. I mean, that is incredibly promising, right? But as the paper is quick to point out, we're still at the very, very beginning of this journey. So, where do AI agents go from here? The paper lays out some really fascinating frontiers. We're talking about agents with way better reasoning skills, with long-term memory so they can handle complex projects over time. Researchers are even looking into ideas like volition and curiosity. Like, can an agent just decide to do something on its own? And then you have the big one, the holy grail, recursive self-improvement. The idea that an agent could actually make its own underlying model better. And that brings us right back to the star of the show, the orchestration layer. This final quote from the paper just sums it all up perfectly. The OL isn't just the body connecting the brain to the world. It's also a kind of scaffold that fills in the intelligence gaps of today's LMs. It makes the whole system so much more capable than the brain would be on its own. Which leaves us with this really provocative final question, pulled straight from the paper's conclusion. If these agents can learn and act and correct themselves, could they one day get to a point where they can improve their own intelligence, kicking off this cycle of rapid advancement? It really is the final frontier for this technology. Look, we've only just scratched the surface today. If any of this has sparked your curiosity about how AI is learning to do things instead of just talk about them, I seriously recommend you check out the full paper. It is a fantastic look at where we are and where we're going with AI. Thanks so much for tuning in.